My dear student, colleagues, and all the viewers who are watching this program live from Facebook page and YouTube channel, I'd like to welcome you all to our International Physics webinar. And today it's our 72nd International Physics webinar. So good afternoon to all. So hope you are well and safe from corona pandemic. So we are trying our best to adjust with this new normal situation. We cannot continue our normal academic program inside the campus. We have to start our online program. Our Department of Physics, Pabna University of Science and Technology, has already started its online program, including online classes and online international physics webinar. And I'm happy to share with you all that we have already completed our 71st international physics webinar, and today it's our 72nd. The main aim of our program is to motivate and encourage our students in this corona pandemic situation. And you have already come to know that in those international physics webinar, physicists from different countries are coming as the main speaker, and they are delivering their speech, and they are sharing their knowledge with our student. And I think by this way our students are benefited. So for those who are new, I'd like to inform that we have divided our webinar into three parts. First, I'd like to welcome and introduce our speaker with all of you, and then our speaker will deliver her or his speech, and at the end we have a discussion session. So today is very important day for our department, and today I'd like to welcome you all through a joint session between Department of Physics, Pabna University of Science and Technology, and the Department of Earth and Space Science, Indian Institute of Space and Science and Technology, IISST, Kerala, India, in astrophysics. And we have with us here today Dr. Anandmayee Madam, Professor, Department of Earth and Space Science, Indian Institute of Space Science and Technology, IIST, Kerala, India, connecting with us from India, and she has already connected with us. So I'd like to welcome our speaker. So good afternoon, madam, and welcome to our International Physics webinar.
Thank you very much. Good afternoon to all of you.
So thanks for accepting our invitation, so madam, and you can start your session now.
Okay, so before I go to the presentation mode, can I say a couple of lines?
Yeah, of course, madam, you can.
Yeah. So good afternoon to all those who are listening to this talk, and I assume that most of you would be students. And usually my talks are pretty interactive talks, but given the situation in which we are, I will deliver my talk, and at the end of it, please feel free to ask your question. I'm not sure in which mode it will be, but I think Dr. Pretam Das will take care of that. And before I start, I am really happy, and I thank Dr. Pretam Das to have invited me. And I will give a talk on my research activities. Actually, I work on star formation, and today I will try to take you on a journey to the stars, and then together we will unravel the mysteries that are there for us to understand and to think and to try to have a research career in this area. So let me go to my presentation mode. Okay, so as the title of my talk says, A Journey to the Stars, Unraveling the Mysteries. So let us first go to a very beautiful thing that we have already, all of us, if you can see the slide that I have shown now, it's a night sky picture. I'm not sure how clear it is to you, but you see a lot of stars. And each one of you, I'm sure, at some point of time in your life, you would have looked up at the sky and you would have wondered at what are these stars and where these stars are, and think beyond, and you would have asked questions about, are we alone, are there civilizations like us elsewhere? So all these questions would have been coming into your mind again and again when you look up at the stars. Slowly, when we get busy with our life, etc., those questions reduce, but still that hunger, that inquisitiveness to know about the stars, the cosmos, the universe, is something which is there in each and every human being. So here, after showing you a night sky picture, let me show you some beautiful pictures which has been taken by others. This is a picture from the US. This shows our Milky Way, that is our galaxy. our own galaxy. In our Indian language, it is known as the Akash Ganga. So you see a huge collection of stars, and you see some dark lanes there. If I go further and show you another beautiful picture which was taken by the Hubble Space Telescope, this is the constellation which is known as the Orion constellation. So you see some very bright stars, and they form a pattern in the sky. And this Orion constellation, the people who have looked up at the skies since long time, and they try to associate the patterns that they see on the sky with some object or animals which are there around them, and they try to give names accordingly. So this Orion is supposed to be a hunter and a dog. Now I leave it to your imagination to find where is the hunter and where is the dog. If you can't, then you can actually try to Google search about the Orion belt and try to figure out. And you also see a host of stars in the background. Another beautiful picture of the Pleiades cluster, which again in the Indian mythology, it is the Kritika cluster. So these are again Hubble Space Telescope images. You see the stars, you see the nebulosities around them. Amazing pictures, and these pictures trigger those questions that I just mentioned. What are these stars? Where are these stars? How do these stars form? Do we have other stars like the sun? If so, then do we have other planetary systems? Do we have another Earth where life exists? So it goes on and on and on. Our questions are never ending, and the universe is also never ending. Now I will show you the picture of our own sun, our own star, the sun. Very beautiful picture taken by again a space satellite. You see a lot of features in it, and you do see something like this during sunrise or during sunset. So these are some pictures of the stars. After that, let us go and try to recollect a nursery rhyme which we have listened to right from when we were toddlers. So twinkle twinkle little star, how I wonder what you are. So you can imagine right from the time we learned how to speak or how to talk, we have been thinking about what these stars are. And at the end of this talk, maybe we will try to understand a little bit of it. Okay? So proceeding further, let us give a formal definition to the stars. So what are stars? How do I define a star? So the moment I tell that stars, this picture comes to your mind, isn't it? We are all used to drawing a star like this. But if I give a formal definition to stars, it is actually a radiating gaseous sphere predominantly made up of hydrogen and helium. Obviously, this is a very unromantic definition to those romantic objects that you see on the night sky and feel so happy about it. But this is it. This is the definition of the stars: radiating gaseous spheres predominantly made up of hydrogen and helium. They are bound by self-gravity. This implies the spherical shape because your gravity is a spherically symmetric force field, right? And they have an internal source of energy. So when I give this definition to the stars, then of course immediately I exclude the planets, the comets. An internal source of energy could be the nuclear energy, which is released during the fusion reaction, which we will talk of in a little while, or the gravitational potential energy, which is released during the contraction of a cloud, which also we will discuss. So now, having given this definition to the stars, one immediately can understand that the stars go through a life, and then they come to the end. And the end comes when either of these two, bound by self-gravity or internal source of energy, is violated. So if they are not bound by self-gravity, means that the star will, gravity will not be able to, there won't be any balancing force to resist gravity, and then you will have a breakaway of the star. Then the next one, the internal source of energy. So if there is no internal source or no supply of internal energy, or there is exhaustion of fuel in the stellar core, then again the star will die. So the definition itself tells us what is the star. It also gives us an idea about that it will go through a life cycle and it will meet an end. Depends upon which of these two properties is violated. It will meet separate ends, like we will see. So now, if somebody asks you again to draw a star, it would be better that you shift from drawing this to a circle. Fine? Okay. So proceeding further, let us see, after defining the stars, let us come to this question as, where do these stars form? I see a huge number of stars in the sky, in the night sky. Then where do these stars form? So stars, if you look at this field again, let me bring your attention to a small blob which is seen here. Now this is the Orion belt again, I repeat, and I zoom on to that small blob which is seen here, and this is the Orion cloud that I have. These are places where stars are formed actually. These are the stellar nurseries. So the stars are born from this gas and dust, which is collectively known as the interstellar medium. The interstellar medium actually manifests in different forms, and this we have different forms and in different phases, and we have the what are known as the giant molecular clouds, and stars form in the dense cores of this giant molecular clouds. This is another example of a giant molecular cloud. You can see the molecular cloud, which looks like a horse head, and hence it is also known as the Horsehead Nebula. And these are places where our star formation is happening. Another picture, these pictures, mind you, are all from the Hubble Space Telescope. That's why you see such spectacular images that we have. These are pillars of creation, or the Eagle Nebula. And again, these are places where our stars are formed. This is another picture where you actually see some black patches in the sky. So originally, when people observed such patches, they thought these are like holes in the sky. But that's not the case. These are very dense and opaque clouds which are sitting there, which are the birth sites of these stars. Why do they look this dark? Because they are so opaque that the starlight from the background does not penetrate, and you just see them as dark patches. And these patches, small, opaque, dark, hole-like patches that were seen, was discovered by one gentleman by the name Bock, B-O-K, and these are also known as the Bock globules. Now, to give a perspective of where the stars form, so you have the giant molecular clouds, the pillars that I showed you, the block globules that I showed you. Then these are which are there in our Milky Way. So you see our galaxy, and these clouds and this dense cores of giant molecular clouds are located there, and these are the stellar nurseries. Okay. So, to give you an idea about the properties of these molecular clouds, so if you have these giant molecular clouds, the sizes are of the order of 10 to the power 18 meters, 10 and 18 zeros. So you can just imagine how huge they are. Masses are around 10 to the power 4 to 10 to the power 5 mass of the sun. And the mass of the sun is around 2 into 10 to the power 30 kg. So these are huge structures, and they are pretty cold. The temperature is around 15 degree K. And then you have this dense cores, like the Bock globules that I showed. You have this dense cores. They are slightly smaller because these are regions in my giant molecular clouds which go on to form stars. So typically 10 to the power 15 masses will be around 1 to 10 solar masses. There could be cores which are of high mass and they could form higher mass stars. These cores typically form low mass stars. When I say low mass, it is around the mass of the sun or slightly more than the mass of the sun. If I say high mass stars, means they are from 10 solar masses above. Okay. So these places, these dense cores, they do not have sufficient temperature or density to start thermonuclear processes. Okay, so they are the starting point, but processes have to go on to bring it to a stage where thermonuclear reactions can start, and hence my star can form. So this is another beautiful image of the same cloud that I showed you. These are the dense molecular cores. And this is a picture in the optical. So you can see completely dark. That means the background starlights are not penetrating. These clouds are opaque to the radiation in the optical part of the wavelength. Now, if I go to the infrared, you will see the background stars. So this slide actually tells that these clouds can be opaque at some part of the wavelength, but you can penetrate these clouds and see what is going on in another part of the wavelength. So these are our sites of star formation. Now, how do the stars form? Having given a definition to the stars, having discussed a little bit about where the stars form, that is in the interstellar medium, that is the stuff which lies between the stars, and a part of that interstellar medium is in the form of giant molecular clouds, and stars formed in the dense cores of these giant molecular clouds. So how do the stars form then? So you have my sun. You have the sun. So let us try to understand how the sun forms. So I said that it forms from such dense cores. So we need to find out how. So what obviously has to happen is clouds need to contract to come to the size of the star. Obviously, the size of sun is around 10 to the power 8, and the size of these dense cores is around 10 to the power 15. So they have to contract and then heat up. So at the core, the nuclear reaction will start. So typically, a dense core of the order of 10 to the power 15 has to contract to the size of the sun. Okay, so I'm giving an overview of a typical sun-like star, how it forms. There are, you can always try to understand how slightly massive or little more massive stars form by taking this analogy. There will be details which I don't want to discuss now. I'm giving a brief overview because this process of star formation is a complete field by itself, and there are highly complicated processes and mechanisms that go on. But we are in today's talk, we are trying to look at it in a very broad way to get a broad perspective of star formation. So having discussed about the sizes of the dense cores, then the size to which my sun is, that is 10 to the power 8 meters, let us visualize or picturize in our head and get an idea about sizes, because that will trigger a lot of imaginations in you in trying to understand how huge these structures are. So let me first show you an image where you see the planets. We are all used to, and many times in the sky we can actually find out where is Venus, where is Mars. In fact, now Mars looks beautiful. So tonight, if you get a chance, please go up and look at Mars. It looks beautiful now. So here you see Earth and Venus, almost similar sizes. Then Mars, Mercury, Pluto. Pluto, I'm putting it as a planet, but now you know that it is not a planet anymore. It has been put in the class of dwarf planets. Now, if I want to look at the other perspective, let me put in the giant planets, that is my Jupiter, Saturn, Uranus. So if I put in my giant planets, then you see that, let me put on my laser pointer. So this is my giant planet, and you see that my Earth is very small compared to my Jupiter. Still, I can see Earth. Of course, Pluto becomes like a dot here. If I go further, I'll put Sun and try to see how my Earth is. Now, if I put Sun here, then my Earth is somewhere like this small dot here. So already you are getting an idea about the size of the Sun with respect to Earth. So Earth for us itself is huge. And now if I put in Sun, my Earth becomes like a small dot. So Sun is a huge body that I have. Now if I go further, let me put in those two, one of those two stars that I showed you in the Orion belt, and another star, the Antares here. So these are the stars that we see, and if you compare the sizes, this is Betelgeuse, that reddish star you saw in the Orion constellation, and this blue is Rigel, which is the bluish star that you saw in the Orion constellation. If you put these stars here, I cannot even put a dot for Sun. A dot will be bigger than the size of the Sun. So only an arrow is shown here saying that 1 pixel will be mostly the size of the Sun. So these are the size scales that we deal with in astronomy, or these are the size scales that we have in the universe. And we are just concerned about stars. Then you have galaxies, you have cluster of galaxies, you have many other things. Okay, fine. Now coming to a little bit of mathematics. Now I showed you these clouds, and I told you that these clouds have to collapse to form stars, or the cloud cores have to collapse to form stars. So a very simple energy balance equation can be derived by taking a portion of, let us first consider the cloud core to be spherically symmetric, because that's the easiest way that we can write down some equations and try to understand. And we take a small element here, a gas element, and we do the balance of forces. Now, if we do the balance of forces, because gravity will act in this direction, then there is pressure from here which will act upwards, and pressure from the upper layers which will act along this direction. Since it is a spherically symmetric case that we have taken, the pressure acting from this side will balance the pressure acting from this side. So if we put on this, if we write down the equation of motion and put a static case, then we get the equation of hydrostatic equilibrium, which shows us that the pressure gradient balances the gravity. Now, if the pressure gradient balances the gravity, then we get what is known as the virial theorem, which all of you would have worked out in your classical mechanics. So what does my virial theorem state? It states that a gravitationally bound system in equilibrium, if we have a gravitationally bound system in equilibrium, then 2 times the kinetic energy plus the potential energy will be equal to 0. So this is sort of a stability criteria. So if this is satisfied, then my cloud is stable against gravity. Fine. So now if I want the cloud to collapse, then I have to tweak that stability criteria and say that 2 times my kinetic energy has to be less than the magnitude of the potential energy. That means my gravity will take over and the cloud core will collapse. Now it is very simple to put in expressions for my kinetic energy and my potential energy. So for a spherically symmetric cloud of constant density, I have U given as 3 by 5 gm square by r, where m is the mass of the cloud core, r is the radius of the cloud core. So I may be calling it as a cloud or a cloud core intermittently. What I mean is a single entity which will collapse and then go on to form stars. Okay, so now the cloud's kinetic energy is given by K equal to 3 by 2 nkt, and n is the mass divided by mean molecular weight into the mass of hydrogen atom. We have already discussed that it is predominantly made of hydrogen and helium. So if we put in this cloud collapse condition, then we can actually derive a minimum mass required to initiate the spontaneous collapse of the cloud, and that is known as my Jeans mass. Just putting in this condition. And as you can see, my Jeans mass, if you look at it, most of it are constants. It only depends upon the temperature of the cloud and the density of the cloud. It is directly proportional to temperature to the power 3/2 and inversely proportional to the density root. Okay, so this, if the mass of the cloud is greater than this Jeans mass, that means the minimum mass criteria is satisfied, then I can initiate collapse in the cloud. In the cloud. So I have shown you pictures of stars. I have shown you pictures of clouds. So obviously, one can understand that there are clouds which are there. Collapse has not started in those clouds. So what maintains equilibrium in the clouds then against gravity? So there are many various reasons. One is the thermal pressure, then there could be rotation. Rotation will resist gravity, resist collapse, then magnetic field, then turbulence. So if I need my cloud to collapse, the core to collapse, then I need to have some external trigger. So I need to trigger a collapse which will eventually lead to star formation. Okay. So now shocks can trigger collapse, right? Because shocks means that my density will increase. Now if density increases, my Jeans mass that I showed you here, let me go back. So shock means density increases. If density increases, this decreases. So the minimum mass criteria can be easily achievable. Okay, so let us go and see what are the ways in which the trigger can happen. So here I'll just pictorially show you that a shock wave is approaching a interstellar gas cloud, which is shown as a blob there, and the shock wave is approaching from the right. And the shock wave passes through and compresses the cloud. Then after it passes through, it sets the cloud in motion, and then the densest part of the cloud become gravitationally unstable and collapse. So these collapsing regions are the places where stars will form. Now let us look at the possible triggers. How can we trigger? I said shock, but shock from where? So let us look at the feedback from previous episodes of star formation. Let me say that I had already a star formation has happened, and I have formed a massive star, and there is a supernova explosion. Please bear with me. I'll come to how the supernova comes at the end state, as the end state of a massive star. But suppose I have a supernova explosion that has happened. That means there is star formation which has happened here, and I have a cold cloud of gas and dust here. So now the shock wave, because of this supernova explosion, propagates and compresses the cloud. And then after the compression happens, what I showed in the previous images, you will have star formation happening. And this is seen also observationally. Shocks from supernova, which comes as the death of massive stars, they trigger collapse in the neighboring clouds. So we know that massive stars, they die young, and hence supernova tend to happen near sites of recent star formation. Now this, except this one, this is just a schematic that I showed, and this figure is from an observation. I'll show you some of the observation from a work done by a master's student of mine. So here what we found that we were looking at this cloud, and we found signatures and observations of a very massive star which has formed. Okay, a very massive star which has formed. We found we did observations in the radio, in the infrared, and we found signatures of star formation here. And then we were looking at various ways to explain and to understand the formation of massive star in this cloud. Then we saw that there is a supernova which is here. And then doing some calculations, we found that this supernova could have triggered collapse in this cloud and initiated the star formation and in this part of the cloud. So it is a triggered star formation, and the triggering has come from this supernova. So going further, let us look at other possible triggers that we have. So again, if there is a previous episode of star formation which has happened, then what happens is, if there is a very massive star formed, these massive stars, their surface temperatures are very high, around 30,000 degree K to 40,000 degree K. And if you look at their spectral energy distribution from simple Wien's displacement law, if you put in lambda m t equal to constant, you will see that there the Planck's radiation curve that I have, the black body radiation curve, it peaks in the ultraviolet part. So when a massive star forms, suppose a massive star forms at a center of the cloud, then there will be a copious amount of UV photons which will be released from its surface. And they will ionize the surrounding neutral hydrogen. And a ionization front can propagate, and once the ionization front propagate, it also compresses the cloud and triggers star formation. So this also observationally another PhD student of mine had worked on, and his PhD thesis was on looking at such triggered star formation because of a massive star which formed at the center of the cloud. So a star formed here and pushed all the matter around because of the massive star. Once it forms, it ionizes the region around it, and a ionization front propagates, and it pushes things to almost circular shape here, and these are places which will be gravitationally unstable and star formation will happen. Okay, this is another work which I did as a postdoctoral fellow. Is there was a star formation here and there was a cloud here, and we could see signatures of this triggering star formation in this. Okay. So another very recent work that my current PhD student worked on, and it's a very recent publication, only 1 week back or 2 weeks back it was published, where we saw that there are two clouds. There are two clouds. One, you can see the bluish cloud, and then there is a boomerang shaped red cloud. So there are two clouds which has collided, and because of the collision there is compression, and we saw a host of young stars forming at the region where they are compressed, which she explained very beautifully in the paper with the schematic. So you have a cloud here, you have a cloud here, and they collide and form a compressed layer here, which is the site of triggered star formation. Okay, so these are some of the ways in which one can trigger and form stars. This is known as the cloud-cloud collision model. Now, let us not worry about how we trigger. Now let us look at that somehow we trigger and we will have star formation. So for a typical ISM values, we can calculate, plug in all the values of temperature, the density, and the rest of the things that if you recollect are just constants. We get that the minimum mass required is 10 to the power 4 solar masses. This symbol is for sun. So the typical giant molecular cloud masses are 10 to the power 5 and between 10 to the power 5 and 10 to the power 6 solar masses. So the question is, does the entire cloud collapse into a single star? Do we have stars of the order of 10 to the power 5 solar masses? Observationally, there are two things which have been seen, that stars always form in clusters. This is a cluster that I am showing you, and I had shown you another cluster also before. So stars tend to form in clusters, and the most massive stars are around 100 solar masses. We don't see stars much beyond this. So definitely something must be happening, which will make us understand both these things, that star formation happens in clusters and The most massive stars are of the order of 100 solar masses, and massive stars are rare also. Okay, so this is the question we were addressing. Does the entire cloud collapse into a single star? Fine. So initially, when we said that there will be collapse, my cloud is not that optically thick. When I say optically thick, this is a term I am using to tell that my cloud is opaque to radiation. In the initial phase, the density is not high. So my cloud is not opaque to radiation. The photons can very freely move through the cloud. Okay, so I have a condition of isothermal collapse. The other thing which I assume that in the beginning is that my density is uniform throughout, which is very unrealistic. You have these huge structures and hence density cannot be uniform throughout, right? So there will be places where there will be density inhomogeneities, which is shown here. Now this will be places of higher density compared to the rest of the cloud. So if these densities are higher, then these will satisfy their genes criteria locally and collapse locally. So you have a big cloud, you can initiate collapse in the big cloud, but then these, because they have higher densities, they will locally collapse. So these cloudlets will collapse. Now again, these cloudlets are not small entities, they are huge. So they will also have density inhomogeneities. So what you have is, again, these will collapse. It will go on and on. You have what is known as cascading fragmentation. Okay, so it is like like fractals. You can imagine that you will have cascading fragmentation. So a big cloud, which was of the order of 10 to the power 4 or 10 to the power 5, you are going down to the cores and clumps that I discussed earlier, which are actually the ones which will go on to form a single star. So from this big cloud, I have this small cores. Let us call them as cores, or maybe the nomenclature varies a little bit between clumps and cores and clouds. Clouds, clumps, cores. That is how the sequence is with respect to your size. Now these are also one has seen observationally. So this is again another work of my current PhD student. So we saw a huge cloud and then we had very high resolution data of that cloud. So we looked at a very tiny portion of that cloud here. And what we saw that tiny portion is also has several of these fragments that I just discussed. So I have the clouds fragmenting. So once the cloud fragments means all these will go on to form stars. So you form stars in a cluster. And then the big one will not form a single star. It will form smaller stars. But the question which you can ask me is, okay, before I go to that, this is another example of a cloud that we see in certain resolution. And when we take observations with much higher resolution, we will see that this one is actually fragmented. These are the fragmented cores of this cloud here. And these are the cores which will go and form the stars. The obvious question which you will pose to me is, does the cascading fragmentation proceed forever? Because these are huge structures. So there is bound to be density inhomogeneities. As long as there is density inhomogeneities, then you should have smaller cores, and hence you should have less massive stars. But typically in our galaxy, we have seen that the stars are of the order of the mass of the sun, or maybe little subsolar, maybe 0.5 mass of the sun. So there must be some process which is stopping this fragmentation. How do we understand that? So initially, as I said, this was my genes mass, which goes as T to the power 3/2 by rho to the power half, and initially it is isothermal collapse. That means my temperature remains constant. How does my temperature remains constant? Because if any energy which is being generated because of the collapse can very efficiently be radiated away from the cloud. And if it is optically thin, the photons will not be obstructed, right? The mean free paths will be longer and hence they will be radiated away from the cloud. Now, and the temperature will be maintained constant. So if this is constant, rho increases because of the collapse. So this decreases. So I go on to have fragmentation. Then what happens is, as the fragments contract, the density increases. Now, when the density increases, the photons will go and hit gas particles. That means the mean free path will decrease. The cloud becomes, or the fragment becomes optically thick. Once the fragment becomes optically thick, what you have is now an adiabatic collapse. So now initially my mj was 1 over rho to the power half. Now if I put in my conditions for adiabatic collapse, I get that my mj is now proportional to rho to the power half. So as my rho increases, mj will increase. So I come to a minimum Jeans criteria. And below that, fragmentation will not happen, and those minimum size and mass cores will go on and form the stars. Okay, so having understood these complications, we will look at the cloud collapse. So my cloud collapses. Initially, I have a slowly rotating cloud of gas which begins to collapse. Now, there is an initial high density at the center, and hence, when I say my cloud collapses under gravity, there is free fall. So now the free fall time scales, because of the slight density enhancement at the core, will ensure that the core collapses faster compared to the surrounding. Now, as it collapses, because of conservation of angular momentum, first it forms a core halo structure, then a disk is formed. So this glowing central part is a protostar which will go on to form my star, and this disk around it, the disk of gas and dust, is known as the protostellar or the protoplanetary disk, and this is where my planets will form. The planet formation is a completely different domain. They form in a very different way. Of course, there are various theories which explain the planet formation, but if you want to imagine it, that this is where my sun will form, and this is where all the planetary system will form. So this explains not only my star formation, but the way my planets form. And then it rotates faster. This is an example that you have of a skater. When it is rotating around, and when she pulls her hands closer to herself, she will start rotating faster. Okay. So now this protostar that is formed, it is completely cocooned or enshrouded in gas and dust. So if you see it if you try to observe it in the optical part of the wavelength, you will not see any signature that a star has formed here. It's completely dark. So stars are very secret about their birth. So they are born deep in cold, dark, and dense, and very optically thick clouds. Their birth is secret at the visible wavelength. But if I try to probe it in the infrared part, where the radiation is transparent, the cloud is transparent to the infrared radiation, I see the first signs of the star being formed. So this glowing piece, which is the first beacon that there is a star forming, is known as the protostar. So what happens is, you have this protostar forming, and there is matter which is being accreted from the surrounding envelope and disk onto the protostar. So we witness, and there is a very complex interplay of the magnetic field which is present there and the accreting matter, and we witness what are known as jets from young stars. So this is a schematic, this is a real observations. It shows a view where the star is forming here, and I am seeing the disk in this orientation. And I see a jet of of matter and radiation which is coming out in this direction. So this is along the polar direction, and this is the disk here. And these are some of the other images taken with the Hubble Space Telescope of young stars and jets from these young stars. A few more pictures to show you that. So this is a very dark cloud where nothing you see. Star formation is happening. A protostar has formed here. And when you observe it in the infrared with the Spitzer Space Telescope, you see these huge jets coming out. Okay? A few more pictures here showing the jets which are accompanied in the initial phases of star formation. And this is another picture of that. Okay. So now I have formed the protostar, but still I have not formed the star. So a protostar contracts, heats up until the core temperature is sufficient that my hydrogen fusion can occur. Once the hydrogen fusion occurs, the energy that is released because of the nuclear reaction will balance gravity. And this process takes around 30 million years for a star like the Sun, and it will be much less for more massive stars. Once my core hydrogen fusion occurs, I say that my star is born. So just to give you an idea about this entire process that I have discussed now, this y-axis of this plot is the energy output, that is the energy per unit time, that is called the luminosity, and the x-axis is the temperature, and temperature increases in the leftward direction. So I start from a clump or a core which goes on to form a star. It contracts, then I form the central part, forms the protostar because of the inside out collapse. Why inside out? Because initially the density at the center was high, so the free fall time scale would be shorter, and once it shrinks or collapses faster than the rest of the cloud, the pressure and density will start increasing, and then the gas pressure will resist further collapse, and you come to a quasi-static spherical object, which is my protostar. So my temperature goes on increasing, then there are various complicated mechanisms which go into play, and finally what happens, the central temperature will be hot enough for hydrogen to fuse, and once that happens, I say that my star is born. So now it attains stardom. So my star is born now. Okay. So what is the source of the stellar energy? I said that it is the nuclear reaction. So stars produce energy by nuclear fusion of hydrogen into helium in the core. And in a sun-like star, this proceeds through the pp chain, that is the proton-proton chain. So you have two protons here, it will form deuterium, and two protons here, deuterium, then this will go on to form your 3 helium, and then you have 4 helium. So my 4 protons or 4 hydrogen atoms will go on to form helium, and this is the source of energy that I have. If I have a slightly massive star, the same proton, the hydrogen atom to helium goes via what is known as the CNO cycle. So carbon and 1H will give you 13N, then again 1H will give you 14N, then again 1H will give you 15O, then it will give 12 carbon back, which acts like a catalyst. But ultimately what I have is my hydrogen to helium through CNO cycle. This happens in a little massive stars because the conditions required, the temperature and pressure required are slightly more compared to the proton-proton reaction. And this gives me an idea about the stellar structure. This is the sun. Similar stars will have similar structure. More massive ones will have slightly different structure. So the flow of energy is from center outwards. Energy is generated via nuclear fusion here, then transported via radiation, then you have convection, and then the pressure and density decreases in this way. Okay. So now what is the journey? The stars are in perpetual battle between forces which are pulling in, that is gravity, and forces pushing out, that is pressure. So throughout its life, like starting from the giant molecular clouds, it is always a tussle between gravity, gas pressure, or radiation pressure. Sometimes gravity takes over, sometimes gas pressure takes over, sometimes gravity again takes over, then radiation pressure takes over. So all this goes on and on in the life of a star. So in a nutshell, if I tell you the sun's story, so these when the stars actually burn hydrogen in their core, they are known as main sequence stars, and the sun starts its life as a main sequence star or as a star here, and it will go through a life cycle where its temperature will reduce but energy will increase. It will become a red giant, then it will become a yellow giant. It will do all sorts of drama, all sorts of curves it will follow. Then it will become a red supergiant. Then what happens is it will eject its outer layers as planetary nebula, and ultimately it will die as a white dwarf. So these planetary nebulas are objects like this. So beautiful object. And the shapes and sizes, of course, will depend upon the energetics and the density structure of the surrounding medium as well. And what is left behind are the white dwarfs. So a sun-like star will end its life as a white dwarf, extremely dense. 1 teaspoon of white dwarf material mass will be around 16 tons. So white dwarfs, the mass is around m sun, temperature is this, luminosity is very low. So a sun-like star will end its life as a white dwarf. It will slowly fade away and blend into the universe. So you can see also the time scales written. So you don't have to worry. It will not happen in your lifetime, your children's lifetime, or your great-great-grandchildren's lifetime. Okay, so there are some billion years for it to happen. Okay, so to give you an idea, this is the sun today. When it becomes a red giant, just the phase after this phase in which the sun is burning hydrogen to helium at its core, this will be the size of the sun. And an idea regarding this size with respect to our planetary orbits, this is the sun now, Earth is here. When it becomes a red giant, it will gobble up all the orbits of these inner planets, and it will be this huge, and Earth will be here. That also will take a long time, so one need not worry. Maybe something else would have happened by then. Okay. So in a nutshell, again, so this is a sun-like star starting from a cloud, will go through a red giant phase, will eject out its outer layers like a planetary nebula, and then go and end its life as a insipid or a very hot object, the white dwarf. But in case of massive stars, it is slightly different. The masses are huge, temperatures are huge, they are more pompous, so their lifetimes are much shorter, and they go through a red supergiant, then boom, it will be a supernova, and what remains is a neutron star or the black hole. And in each process, they give back to the interstellar medium, and hence this entire process of star formation is a cyclic process. The next generation of stars will form from these clouds, which have been enriched by the end state of these stars. And if you look at the evolution of the sun, I showed it goes through a lot of drama, up and down in that curve. But the higher mass stars are pretty simple. They go boom in one horizontal direction like this, because the nuclear reaction at the cores will be so fast that the outer layers don't get time to react to it. Okay, now before we go on to the last part and try to understand, we'll just try to see what is the composition of the interstellar medium. And as we can see, hydrogen and helium are by far the most abundant elements in the universe. But from where do we get these elements? And what about the other elements that we see? Let us try to understand that. So if I draw a periodic table, this is the very simple periodic table of an astronomer. So you have hydrogen, the abundance we write it as X, helium Y, and for us rest of everything is called metals. For us anything heavier, any element heavier than helium is metal. So we have a very simple periodic table which the chemistry people will not like, the other physics people will also not like, because this is what our periodic table is. Even if we give a very simple approach, we need to know from where all these elements have come. These have come, of course, from the Big Bang, but from where has all these elements come? So we look at the nucleosynthesis in the cosmic kitchen. So as the sun evolves, what happens? First, it is burning hydrogen to helium in its center. After that phase, helium will be completely burned. You will have inert helium here and a shell which will burn hydrogen. After that, your helium burning will start at the core, hydrogen burning will be in the shell. Okay? And then you will after helium burns to carbon, you will have an inert carbon core. Then you will have a double shell burning. One helium will be burning, hydrogen will be burning. So already, as you can see, I started off with hydrogen, but I have produced helium, I have produced carbon. So some processes happen. A little bit of what has been cooked up in the stellar interior does come out to the interstellar medium and through the planetary nebula, but very minute part. Most of it is locked in this white dwarf that you see. So low mass stars does not contribute much to the enrichment of the interstellar medium, from where next generation of stars form with heavier elements. But what happens in the massive stars? You can see that hydrogen to helium, helium to carbon, then to oxygen, neon, manganese, silicon, everything goes on up to iron in the cores of the massive stars, because the temperatures are high and these nuclear reactions can happen. Okay, so if you look at the structure of a massive star, it is like an onion ring here. So you have the hydrogen, and the envelope is hydrogen, but if you look at the core, it will be everything up to iron. So you will have nuclear burning processes which happen. So nucleosynthesis happens. Of course, it stops at iron because that's the most stable element that you have. And to go beyond iron, if you look at this plot of my binding energy per nuclear particle versus the mass number, this is the domain of fusion that I talked up to iron. But if I want to go to heavier and heavier, it is an endothermic reaction, right? So you have fission here. So in massive stars, like stars which are greater than 8 solar masses or so, the core we can have elements can be fused up to iron. Then the iron cores do not immediately collapse because there's a lot of electrons which are also generated, and they have what is known as the electron degeneracy pressure, and they resist collapse. This electron degeneracy pressure will oppose the collapse, or they will resist gravity. So if the density becomes very high, because it is a very, very dense environment that you have there, if the density continues to rise, then the electrons are forced to combine with protons to form neutrons. Now the electron degeneracy pressure will disappear and there will be a catastrophic core collapse. And what happens? The core violently collapses until you have only neutrons there, where then the neutron degeneracy pressure will kick in. Earlier you had electron degeneracy pressure, now you have neutron degeneracy pressure that kicks in. Then the core bounces when it hits the neutron limit, huge neutrino release will be there, and the infalling matter, because it is collapsing, will meet the bouncing core. A shock wave will rip through the star and there will be explosive nuclear reactions, and the outer parts of the star will be completely exploded and blasted outwards, and you will have a supernova. And what remains behind is either a neutron star or a black hole. So this is my core collapse supernova. You can also have a supernova when you have two white dwarfs in a binary system, a carbon white dwarf. That means at the when the core has become inert carbon, no more nuclear reaction happens, and it is held together by electron degeneracy pressure. And if carbon burns under degenerate condition, because if you have a binary system and one of them is accreting matter from the other, then the condition becomes very unstable. There is something called the Chandrasekhar mass limit, and if the mass exceeds that, then equilibrium cannot be maintained, and there also you can have a supernova event. So you can have a core collapse supernova, which is known as the type 2 supernova, or a supernova in that condition. So once the supernova happens, these are some of the images with Hubble Space Telescope of the supernova. Can I take 5 more minutes, Pretam?
Yeah, you can.
Yeah, so supernova event that happens, these are some supernova here. So it can actually outshine the galaxy. They are very energetic and very bright events that happens. So this gives us a time scale of how each nuclear burning phase happens. Then you can see that towards the end, it is only 0.1 to 10 seconds, which within that this explosion happens. So these hydrogen burning takes 10 to the power 6 years, helium burning 10 to the power 5 years, carbon burning around 600 years, 1 year, 6 months, silicon burning 1 day, core collapse is in seconds, core bounce is in milliseconds, and the explosion is in 0.1 to 10 seconds. So these are the time scales in which the supernova explosion happens. Now in the supernova explosion, so till the supernova we have formed till iron, right? Now, what about the other heavier elements? So in the supernova explosion, we have huge neutron flux. So this neutron capture can happen, and we can form heavier and heavier elements beyond iron by what are known as the R process and the S process. Mostly the R process in the core in the supernova cases. So now the best guess for the nuclear origin of the elements, this is the periodic table that has been generated by the astronomers. So as you can see, it is color coded, showing its origin. So you have these hydrogen, helium from the Big Bang. Then you have all these elements, sodium, magnesium from exploding massive stars. Then low mass stars are like carbon, nitrogen, etc. You see gold. All of you must be wearing some gold or the other, AU. This gold is actually formed in merging neutron stars. And you can also see what are the things like chromium and all in exploding white dwarfs. So this gives us an idea about where these elements that we so casually look at the periodic table or wherever we see around us, their origin actually is in the stars. So now let me show you a thing which all of you must be looking at. When will this talk end? This is the iPhone that you would be having. So let us look at it. Plastics, which is carbon, sulfur, oxygen, nitrogen. The glass, which is silicon, oxygen. Case, aluminum. Wires, copper. Connectors, tin, silver, gold. And many other things which go into your iPhone. Or let me show you the dress that this king is wearing, or the material with which we are made. Everything we owe it to the stars. Whatever we see, we owe it to the stars. It has been cooked up in the cosmic kitchens, either in low mass stars or in the high mass stars, or mergers of compact objects like the neutron stars. So coming to the end of my talk, so we started off with Twinkle, Twinkle, Little Star. How I wondered what you are. But now I end by saying, Twinkle, Twinkle, Little Star, now I know what you are. So the theory of the star formation, the nucleosynthesis, everything takes us into a very different level, into an unearthly level. And if there were no observations, all of you must be thinking that whatever I am telling is just a story. And I'll try to end by saying thank you to the stars for creating the stuff that makes our cell phones, which is, I think, the most important part of our lives now. And to end with a note by Carl Sagan, the nitrogen in our DNA, the calcium in our teeth, the iron in our blood, the carbon in the apple pies which we have burnt while we were trying to learn cooking, I would say, during lockdown, were made in the interior of collapsing stars. We are all made up of star stuff. So thank you for your patience, and I show you a picture of my institute, which is India's only university focused towards space science and space technology. It is Indian Institute of Space Science and Technology, which is the academic wing of ISRO, which is India's space research organization. And thank you. I'm open for
Thanks,
questions now.
thanks, madam, for your wonderful and exciting presentation. And the students have learned a lot of things. So we have got some questions. So if you allow, we can start our discussion.
Sure,
So
definitely.
the first question, is it possible to form star from supernova?
Okay, supernova is actually the end state of massive stars. So stars that are more massive than 8 times or 10 times the sun, they end up as supernova. So when supernovas form, they expel heavy elements into the interstellar medium. And then the interstellar medium, the next generation of stars form from there. So supernova are the end state of stars. Okay.
Thank you, madam. So we have got another question in comments. So is it possible for a star to turn into planet, and where is the center of the universe?
Okay. Where is the center of the universe is a very difficult question to answer. And I don't think there is a answer to that, because the universe is accelerating, is expanding and accelerating. So to find the exact center of the universe is difficult. But the other question that you asked, the stars cannot turn into planets. If you remember, I said the cloud, the central part forms the protostar, which goes on and forms the star. The other part, the envelope flattens into a disk because of conservation of angular momentum, and from this disk the planets form. So they are two separate things, and their formation mechanisms are also different.
Thank
Okay.
you, madam. So we have another question. What keeps the sun spinning?
What can you repeat?
What keeps the sun spinning?
What keeps the sun spinning? Okay, so as you would have realized, when I said that when the cloud is rotating and contracting, it rotates faster, right? And that is when the star has formed, and it continues to rotate unless there is some other tidal interaction which can happen and it will alter its rotation. The sun will rotate because it has formed from the collapse of a rotating cloud.
Okay, madam. So thank you. So we have another question. How the various elements are formed in star or in a planet?
Okay, various elements do not form in the planet, they form in stars. As I said, as the star forms, right? When the star forms, in the core, hydrogen fuses to helium. Now, after that, depending upon the temperature and pressure and the mass of the stars, you will have various elements forming. Like I showed, in a massive star, after hydrogen, it will be helium, then helium to carbon, carbon to nitrogen, nitrogen to oxygen. It goes all the way to iron in fusion reaction. Beyond iron, it goes via neutron capture reaction. So these are all which forms in the cores of the stars, and beyond iron, heavier elements are formed in neutron capture reactions, which happens during supernova events. Inside the planets, the there is no nuclear reaction happening, right? So they don't form there. So the constituents of planets is because of the whatever is there in the planetary disk from where they have formed. There is some radioactivity goes on, but no nuclear reactions don't happen.
Thank you, madam. So we have another question. Can you expect in near future we can find some elements beyond today's periodic table which can be found inside star?
Yeah, yeah, maybe. Yes, more and more research into the nucleosynthesis. Maybe we can, with more observations, we may discover. Yeah, why not?
Thank you, madam. So we have another question. So what is the last element in a supermassive star other than iron?
Beyond iron, there are so many heavy elements that I showed in my astronomer's view of the of the periodic table, right? So these are the things which are formed. Like you see in the merging neutron stars, you have I don't know what are these elements. Thorium is there. Then HO, DY. You have to find out what are those. I do not know. Platinum, bismuth, all are there. Okay. Yeah.
So thank you,
But
madam. We
beyond
have
iron,
another.
it is with
Yeah.
neutron capture. Yeah.
So we have another question. So have the approaches and analyzing methods changed at all related to different astronomical events after the detection of gravitational wave?
Yeah, gravitational wave is a wonderful branch of astronomy which has now it's at its peak actually, or maybe peak is away, but wonderful astronomy that we have, and only from there that people understood about merging neutron stars, right? So the approach has definitely changed. What we knew till the detection of gravitational waves is from the photons that are coming to us. Now there is now is the era of multi-messenger astronomy. Photons are coming, gravitational waves are coming. So we have the huge universe in front to unravel and understand. Yes, things have changed, things have improved definitely.
Thank you, madam. We have another question. So can we form those elements in laboratory in the same way as we have seen inside star?
That would require the conditions, right? In the laboratory, can you have those conditions?
Can elements be formed by collision of star?
Yeah, merging of neutron stars, because you need neutrons, you need sufficient temperature, you need energy. So that's what I said, the gold that you are wearing, or the gold that you are your family, you would see people wearing, that is formed in the merging of neutron stars.
Okay, so thank you, madam. We have another question. What is the starting moment of star formation in nebula?
Starting moment, when I say star formation, means a star forms when at the end of a protostar has formed, and when at the core the hydrogen fuses to helium. That is when I say a star has formed. But if you want to say when it starts, so you have this gravitational this giant molecular clouds. When collapse initiates is the starting point of star formation, because it has to collapse, then fragments will form, then further fragments will form, then the cores will form, and then that core will again collapse to form the protostar and the protoplanetary disk. And in the protostar, at the core, temperature will be high enough to fuse hydrogen to helium.
Thank you, madam. So we have another question. So what's the expected time to get our planet gets cool in her core?
Can you repeat, please?
So what's the expected time to get our planet gets cooled in her core?
Okay, now that is a very different question altogether, because it is already we have a planet which has formed, so the temperature structure is already there in Earth, and because of that temperature structure, you have the core which is in the liquid form, right?
Yeah.
So that is a different. I think that will be more of a geological thing rather than from the star formation. Yes.
Thank you, madam. This may be the last question. So, how much advancement in laser technology or improvement in telescopes do you expect, which will help in getting more precise result in observational astronomy in near future, maybe in the next 15 to 20 years?
Oh, you will see a huge thing in the next 5 years, by 15 to 20 years. There are many space missions planned. In India, also many space missions are planned. Big telescopes are coming up. In Hawaii, a 30-meter telescope that is called the TMT is coming up. So, in the next by 15, 20, in the next 5 years also, you will see a huge advancement in technology for observing, because observations are extremely important to validate the theory, right? So,
Yeah.
yeah,
So, thank you, madam. So, one more question I have got. So, if you allow, we
yeah.
can read.
Sure, sure, I'm
Okay.
there.
So, how so many elements is as available in Earth?
Yeah. So, as I told you, when this supernova events happen, so supernova in the supernova events, which are the end state of massive stars, heavy elements that has been formed due to nucleosynthesis is dispersed to the interstellar medium. So this interstellar medium then mixes, and you have the giant molecular clouds. And again, the next generation of stars will form from the enriched giant molecular clouds, which are enriched with heavy elements. So again, the same process, the next generation will be more enriched with heavy elements, right? So when the star forms and you have the protoplanetary disk around it, it when our sun formed, it formed from a cloud which was enriched with this heavy elements, and the inner part formed the sun, and from the protoplanetary disk the earth formed, right? So it was from this enrichment that all the naturally occurring elements have come.
So thank you, madam, for your wonderful lecture and exciting discussion session. I think students have learned a lot of things about the star, and they have come to know the mysteries of star formation and their lifestyle. So thanks again, and we'd like to say thanks on the behalf of the Department of Physics, Pabna University of Science and Technology. So we are very grateful to you that you have accepted our invitation in this Corona pandemic situation, and our intention is to motivate and encourage our students. And I think they may be motivated by your lecture. So thanks again.
Okay, thank you, Pritam, for inviting me. And I usually try to excite the students. And my email is there, page at iist.ac.in. Any student wants to contact me regarding a career in astronomy or to even ask some doubts, please you can share. They can write to me, no problem.
So one more question. So from
Yeah.
student, I can
Yeah.
ask on the behalf of them. So what are the opportunity for foreign student to apply for masters and PhD in your institution?
Uh, yeah, for masters and PhD, we do not have any foreign student as of now, but uh, there should not be any issue with masters and PhD at the undergraduate level, because we have a ISRO absorption, so only Indian citizens are concerned. So because our undergraduate students, if they perform as per our one criteria set, they are absorbed in ISRO. But for the postgraduate and PhD, there is no bar.
Okay. So thank you, madam. So
Yeah.
hopefully in near future we'll arrange another webinar with you, madam. So
Sure, sure.
we,
Any other topic also will be.
okay.
I'm very happy to discuss always with the students, and even situation improves, I would love to
Yeah,
come to
yeah.
your university
Okay.
also.
I'll definitely invite you after the COVID. So thank you, madam. So bye for today.
Okay. Okay. Thank you,
Bye.
Pritam, and bye to all the students, and very happy puja to all of you.
Yeah.
I know in Bangladesh also it is equally
Yeah.
important as in India. So enjoy.
Okay.
Okay.
Happy